the CS direction that I have just discussed. So it turns out that Goten and Nosat's Quiver bundle is an instance of the notion of tensor product of Quiver representations that I study in my work. So this is today's agenda. So first I will start with some basic definitions and notation. Then I will discuss on the representation theory of tensor quivers and define this notion of tensor product of quiver representations I will be working with. Then I will briefly survey the construction of the moduli space of quiver representations for classical quiver representations and the gauge theoretic quiver vortex equations. This with the aim at the end of the presentation presenting some applications, or better said, incarnations of these tensor products in mathematics. So is everything all right in the...
I think they are only seeing the first slide. So now we are on, but it's only sharing the first one.
Maybe you can share the slides and
He's already sharing, but sì, questo sì.
So and what's
presentation this time. O importante é que funcione no computador nosso, não é no computador do visitante, não é? O importante é funcionar no nosso computador. Isso é o que tem que tentar funcionar.
you don't see my screen anymore, right? In the Teams.
What?
Que outros veem? O que é importante é que funcione no computador nosso, não é? Se nesse computador não funciona, temos que comprar um computador para sempre, não é?
Are you seeing my screen?
Oh, yes, only the first three.
Only the first slide. Okay, so I think I will not seem to do the issue. Okay, so let me just bring this here. I mean, now you should be seeing it on the Zoom, right?
Can you send me your slide?
Yes. Okay, hold on, let me try just one more time.
If you send them to me, I can share them.
Now you should be seeing it on the Zoom, on the Teams, or not.
Always the first slide. Can you? Yeah, now we see.
Now it's in this,
yes, all of them.
All of them.
Yes.
Okay, sorry. Okay, so sorry. So this is the agenda for today, as I was telling you. And so now let me start with some basic definitions. So, then.
É preciso tirar o som.
Sim.
Okay, so a quiver is a finite oriented graph that is a tuple VE HT, where B is a finite set of vertices, E a finite set of edges, and H and T maps that assign to an edge corresponding to head and tail. So a path in a quiver is a sequence of edges, alpha 1 up to alpha k, such that the tail of the edge alpha j equals the head of the edge alpha j plus 1. We will be denoting the trivial paths, which are those paths that start and finish in a given vertex of the quiver as EI. So, for example, if I consider this quiver here, we have with two edges, then the, for instance, tail of beta equals head of alpha, which is equal to the vertex 2, and all the non-trivial paths for this quiver will be the path alpha given by the edge alpha, the one given by the edge beta, and the one given by the composition of alpha and beta. Those are the only paths in this quiver. Good. So now representations. So we fix a ring space XOX, and we fix a family of OX modules indexed by the edges of the quiver. So a twisted representation is a tuple given by the following data. So to each vertex of the quiver, I will be assigning an OX module. And to each edge of the quiver, I will be assigning a morphism between the OX modules that I have previously assigned to each one of the edges, but I twist this morphism by the corresponding twisting module M alpha in the family M. Okay? So a morphism between twisted representations will be given by a family of morphisms of OX modules indexed by the vertices of the quiver, for which the diagram that you see here in the slides commutes. So an important property is that the category of twisted representations of a quiver Q is abelian, meaning that we can use all the tools coming from the homological algebra, to study these representations. Okay. Just 1 minute. So an example. Okay, so you can choose to work instead with the representations in the with representations in the categories of covariant sheaves over Keller manifold. If you take X to be XOX to be a Keller manifold with its sheaf of holomorphic sections, and same for in the algebraic category, working with quasi-covariant sheaves over an scheme. Okay, so an example of twisted quiver representations is that of Higgs bundle. So let me remind what a Higgs bundle is. So we take a Riemann surface X. So a Higgs bundle is given by the data of a holomorphic vector bundle over the Riemann surface X, and morphism, the morphism of this holomorphic vector bundle twisted by the canonical vector bundle, line bundle in this case of the curve. Such an object can be regarded as a representation of the Jordan quiver that you see here in the slides, a twisted representation of this quiver for which the twisting module is the dual of the canonical bundle of the curve. Okay? So when studying the representation theory of quivers, it is more useful to study instead modules over certain algebra. So what is this algebra? In this case, it's called the path algebra of the quiver. So let me define in this situation how this algebra looks like. So for a non-trivial path, P in the quiver, we define the twisting module MP to be given by the tensor product of the twisting modules associated to each one of the edges in the path. If the path that we are taking is the trivial path, then we set the twisting module MP to be the trivial OX module. So the twisted path algebra of the quiver cube is the sheaf of OX algebras whose underlying OX module is given by the direction running over all paths of these MPs with product rule given as follows. So if I take a local section MP in the twisting module MP, then its product with a local section MQ is going to be equal to the tensor product whenever the head of the path Q equals the tail of the path P, and it's going to be 0 otherwise. Good. So let me define now the notion of module over this path algebra. So a left module over the twisted path algebra is an OX module which has, and sorry for the redundancy, which has a compatible structure of module over the twisted path algebra. And by this, I mean that there exists a structure map, which is an OX linear map that goes from the tensor product of the twisted path algebra with M into M, for which the usual actions of modules over algebras hold. There is as well a notion of morphism of modules over the twisted path algebra. So a morphism is an OX linear map which is compatible with the structure morphisms for each one of the modules M1 and M2. And this compatibility condition is expressed by asking the diagram that you see here in the slides to be commutative. Good. So now this result, which is due to Bartocci, Bruzzo, and Rada, tells us that there is an equivalence of categories between the category of left modules over the twisted path algebra and twisted representations of the Quiver cube. So this is a generalization of the well-known fact that we know for classical Quiver representations, which I will sort of discuss now. So I will give the idea of how this works for classical Quiver representations, and this result is essentially a shift version of this. So how do I go from a module to a Quiver representation? Well, I just take these are going to be like the vector spaces that I assign to each one of the Quiver, and the morphisms between this I will call M. And the morphisms are going to be given by simply multiplying by the edge alpha, multiplying this element M by alpha, and using the action of the coming from the structure of module. How I go the other way around. So if I start with a representation, a linear representation of a Quiver cube, then the corresponding module will be given by the direct sum of all these guys, and the modular structure will be given by the action is determined by action of alpha is given by the morphism F alpha. Okay, so this is how it works in the classical setup of Quiver representations, and yeah, it is almost the same idea in this situation of twisted Quiver representations over I'm working with OX modules. Okay. So another key ingredient in our notion of tensor product is that of Quiver representations with relations. So let me define what a relation is. So a relation on a Quiver cube is a formal sum running over all paths of length greater than 2 with fixed tail and fixed head of terms of the form Cp times P. So Cp here is a global section of the structure sheaf of X, and P is simply like a formal term. Okay? So given a set of relations, I can build a double-sided ideal of the twisted path algebra by taking a set of generators for this ideal, a subset of these sets Ru, which I cook from the relations by replacing each one of these terms P by local sections in the corresponding twisting modules. Now, before defining what our representation with relations is, let me recall that because of the equivalence of categories that I have just described, tensorization by a local section MP induces a map between the OX modules at the tail and the head of this path. So, having this in mind, I define a representation to, I say that a representation satisfies the relations in R if for all relation generating the ideal IR, the corresponding morphism between OX modules is equal to 0. Okay, so now a natural question is if there exists some sort of equivalence of categories in the same spirit of the one that I have just discussed, and the answer is yes. But let me first hit you up with this proposition. So restriction of scalars gives a full embedding of categories between the category of modules over the quotient of the twisted path algebra by the ideal of relations and the category of modules over the twisted path algebra. And now the result is that there is an equivalence of categories between the category of twisted representations with relations and that of relations, of modules over the quotient of the path algebra, and that this equivalence of categories is compatible with the one that we have before, in the sense that the diagram of functors that you see here in the slides is commutative. So let me remark that the right-hand side functor that you see here is this full embedding of categories described in this proposition. Okay, so tensor quivers. Are there any questions so far?
Yes, I'm sorry. What is meant by restriction of scalars in this case?
Restriction of scalars.
It's typically when you go to a subring or something, right?
I mean, whenever you have like a ring morphism and you have two modules over this ring, you have two functors, one given by restriction of scalars and the other given by extension of scalars. And this is the same that is happening in this equation. Good. So tensor quivers. So the last ingredient before giving our definition of tensor product. So given two quivers, I define the tensor product quiver, also known as Cartesian product of quivers in the literature, as the quiver given by the following data. So the set of vertices of this new quiver will be given by set of vertices of the first quiver times set of vertices of the second quiver, and the set of edges is going to be equal to set of vertices of the first times set of edges of the second, this joint union with set of edges of the first times set of vertices of the second. So, for instance, if alpha is an edge of the first quiver and j is a vertex of the second quiver, then the head of such an edge is going to be given by the vertex head of alpha, comma j, and so on. Okay, so perhaps this construction is better seen through an example. So here in the slides, you can see what the product of two type A2 quivers would look like. Okay, so for instance, the tail of the edge 2 beta would be the vertex 2, 1, because the tail of the vertex beta here in the first quiver is the vertex 1, as you see here, so, and so on. Okay? Good. So now I am going to relate the path algebra of this quiver, Q prime tensor Q double prime, with the path algebras of Q prime and Q double prime. So this reads as follows. So we have an isomorphism between the tensor products of the twisted path algebras of Q prime and Q double prime with the path algebra of the tensor product quiver modulo some ideal of relations. So let me explain what is the twisting, both the twisting and the ideal of relations that I am using on the left-hand side. So for an edge of the form alpha j, where alpha is an edge of the first quiver and j is a vertex of the second quiver, the twisting module is going to be equal to the twisting module m prime alpha. And similarly for all the edges of the form I beta, where I is a vertex of the first quiver and beta is an edge of the second. So now I is the ideal of relation generated by all these difference. But I don't want to enter in the details of what is what, but I do want to say that what these relations are trying to capture is the following. So in the tensor quiver, we have the following. Locally, it looks like this. So what these relations are telling me is that if you follow this path on the tensor product quiver, is the same as going through this path. So this is what we are exceptionally trying to capture with those relations here in the slides. Okay? So now we are ready to discuss on what the tensor product of quiver representations is. So we start with two representations, E prime and E double prime. So to each one of these representations, because of the first equivalence of categories that I had, I can assign modules over the corresponding twisted path algebras. Now, the tensor product of these two modules has canonical structure of module over the tensor product of the twisted path algebras. But because our previous proposition, this is the same as having a module over the twisted path algebra of the tensor product quiver modulo some ideal of relations. And this, because of our second equivalence of categories, is the same as having a twisted representation of the tensor product quiver with some relations. Okay? So perhaps this is better seen again through an example, and in this example, I am going to consider the case in which all the twistings are trivial. So if we take our twisting modules to be trivial, then the tensor product of two representations will look locally as you see here in the slides. Okay? So in particular, if we restrict ourselves to the classical case of linear Quiver representations, we recover notions, the notion of tensor product that has also been studied by Herschen and Das and collaborators. Another interesting example that came to me recently is that if you consider, for instance, tensor products of Quiver representations for a Quiver cube with type A2 Quiver, then representations of the tensor product of representations of these two quivers will be equal to, will give morphisms of representations of Q. Yeah, between representations of Q, which I think it's really interesting. Okay, so now I will survey perhaps things that are already known for some people. So for now on, for simplicity, I will restrict myself to Quiver bundles, which are representations of quivers in the category of holomorphic vector bundles over a Riemann surface X, or I will be either considering classical Quiver representations, which is the case where X is a point and the representations take values in finite dimensional vector spaces. So given, and I will be considering untwisted representation just for simplicity, but in the article, let's say that most of these results are written for the more general framework of color manifolds and twisted representations. So given a representation of Q and a stability parameter, which is a vector with real entries indexed by the vertices of the quiver, we define the theta slope to be given by the quotient that you see here in the slides. So you can see this as an hybrid between the usual stability condition for vector bundles and the usual stability condition for classical Quiver representations. So with respect to this notion of theta slope, I have notions of semi-stability for sub-representations and also of polystability. So recall that representation is polystable if it can be written as a direct sum of theta stable representations, all having the same theta slope. Okay, and now I will concentrate on the case of linear Quiver representations. So let me recall how the moduli space is constructed in this situation. So we fix a dimension vector, D, which will parameterize the dimensions of the vector spaces that are assigned to each vertex of the quiver. So the D-dimensional representations of my quiver will be parameterized by this affine space, and the reductive group, GLD, which is given by the product of some copies of general linear groups, will be acting on each component here by conjugation. So Mumford's GID will give me moduli spaces for semi-stable and stable Quiver representations. So the GIT quotient on the right classifies as equivalence classes of semi-stable representations up to just as equivalence classes, which is the same as classifying polystable representations modulo isomorphism. The left-hand side quotient, which is actually a geometric quotient, classifies isomorphism classes of stable representations modulo isomorphism. And this quotient is smooth, and it is an open dense inside the moduli space of semi-stable representations. There is a symplectic point of view on this construction. So on each component of the parameter, on the parameter space of representations, I have the Hermitian metric that you see here in the slides. And yeah, and I will be considering the action of the unitary group on this parameter space by conjugation as well. Another important thing is that the parameter space is a Keller manifold with symplectic form given by -2 times the imaginary part of this Hermitian metric. So, as I was saying, there is an action by conjugation of the unitary group on this space of representation, and this action is Hamiltonian, meaning that there is a moment map. And in this case, the moment map is sending a representation of my Quiver Q to this family of commutators indexed by the vertices of the quiver. Okay, so now the following result, which combines results of King, Hoskins, and Wilkins, sorry that I forgot to put Wilkins reference here, tells me that there is a homeomorphism between the moduli space of semi-stable Quiver representations that I obtain using GIT and the moduli, and this symplectic reduction. So here I have denoted mu inverse of theta as the set of representations of the Quiver Q that satisfy the following equation. So here I am denoting like this commutator that you see there in the construction of the moment map equals to stability parameter times the identity. So I take the solutions to this equation modulo unitary transformation, and this is the symplectic reduction that I am considering. So yeah, this is some sort of a non-projective version of the classic Kempf-Nest theorem, if you want to think, if you want to look at it in those terms. So in the same spirit, we have like an infinite dimensional analog of this situation, which is known as the Hitchin-Kobayashi correspondence for Quiver bundles. So here I will be working when X is a curve. So this result, which is due to Oscar Garcia Prada and Luis Alvarez Consul, tells me that a Quiver bundle is polystable if there exists an Hermitian metric for which the following PDE holds. Right, so let me explain what is what here. So here, Fi is the, okay, sorry. Yeah, sorry. So maybe I misspoke here a little bit. So yeah, so Quiver bundle will be polystable if we can find an Hermitian metric Hi on each one of the vector bundles for which this equation holds. So Fi here is the curvature of the Chern connection associated to the metric, and lambda is the contraction of Pareto with respect to a fixed scalar form on the curve X. So why I was saying that this is a result in the same spirit of this Kempf-Nest result type that I explained before, because this gauge theoretic equation is no more than a moment map condition in infinite dimensions, right? Because it is both combining the moment map for vector bundles of Atiyah Bot, which is the first term, and the moment map coming from Quiver side of King. So yes, so this is why I was telling you that. Okay, so now applications. So the first application is that if you tensor two polystable Quiver bundles, then the representation of the tensor product that you will get will be polystable for a stability parameter that depends both on the stability parameter of the first Quiver and on the second Quiver. So as a corollary, so actually in the paper, this is written for an arbitrary like Keller manifold and twisted representations. So in particular, the Keller manifold that you can take is a point. So in this situation, we recover this result, which says that tensor product of polystable classical Quiver representations is polystable. So at this point, like several questions arise. So for instance, does every polystable representation of the tensor product Quiver arise as tensor product of polystable representations of Q prime and Q double prime? What sort of analytic or algebraic structure does this set of decomposable tensors or representations has? For classical vector spaces, we know the answer, right? Because the Segre embedding tells us that, okay, I can describe the set of decomposable tensors, right, as variety inside this higher dimensional projective space, right? So, inspired by this result, we managed to see like an analog of the Segre embedding for this tensorization of representations we are dealing with. So we have to first prepare ourselves for this. So we choose stability parameters such that the corresponding symplectic reductions are complex Keller manifolds. So here I am looking at the moduli space of Quiver representations from the symplectic point of view. So our previous result, or our previous theorem, tells us that there is a well-defined equivariant map between the set of polystable representations, right? And since this map is equivariant, it descends to the moduli spaces. And the result is that this map is an embedding with image submanifold whose real dimension depends on the Euler forms of the Quivers Q prime and Q double prime. Under certain conditions, for instance, asking the genericity of the stability parameters that I'm considering, and for instance, also asking our Quivers to be acyclic, this map is actually algebraic, and the algebraic analog of an embedding will be a closed inversion. Okay, so this is the result, and now let's use this to actually recover this Segre embedding from this Quiver perspective. So if I study the moduli space of representations of one-dimensional representations for the Kronecker Quiver with m arrows with the stability parameter, with respect to the stability parameter -1, 1, then this moduli space can be seen to be isomorphic to a projective space of dimension n-1. Same if I repeat the same exercise for the Kronecker Quiver with m arrows. So now, what if I study the moduli space of representations for the tensor product of these two Quivers with respect to the stability parameter -2, 0, 0, 2? So if you write down what the GIT quotient would needs to be, you find out that this is going to be a projective variety of inside the projective space of dimension 2n m -1, cutted by these equations that you see here in the slides. So now let me put all together. So first, we know that the tensorization of representations induces a map between the moduli spaces that I have just described, and that this map is a closed immersion. And moreover, we know that whenever I tensorize like two representations, the representation that I get will be a representation with relations. So if I put the moduli space, this moduli space, by the equations, which are these, like these are the equations defining the relations, then the subvariety that I will be getting is actually the subvariety that the Segre embedding describes. So yeah, it's really, really nice. Okay, so that was, let's say, an application to the application. And finally, I would like to discuss a relation between these tensor products with character varieties. So I will be considering the variety of the mutant matrices of the times the matrices, commuting matrices, modulo the action of the general linear group. So this is the same as looking as representations of the Jordan Quiver with himself with some relations, right? So now we can see that the tensorization of representations induces a map from the moduli space of representations of n-dimensional representations of the Jordan Quiver times the moduli space of n-dimensional representations of the Jordan Quiver into the variety of commuting matrices modulo the action of GLP. Okay? And how does this relate with character varieties? Well, so I'm going to that, but first let me recall what a character variety is. So the GLN character variety for the free abelian group CR is the GIT quotient given by taking the representation variety modulo the action of GLN by conjugation. So I will denote this character variety MRN. So now I can see first that the character variety M1N sits inside the moduli space of n-dimensional representations of the Jordan Quiver as an open affine subscheme. And same for the character variety M2N. N2MN inside the moduli space of commuting matrices, modulo the action of the general linear group. So, tensorization map descends to this affine scheme, and since this fiber product here is irreducible, the C-theoretic image of this map will be as well irreducible, right? But what about the scheme theoretic image? So the scheme theoretic image will be the scheme sitting inside the rank 2 character variety, sorry, the character variety M2MN, determined by the kernel coming from the induced ring map in coordinate rings. And one can see that as a topological space, the scheme theoretic image will be the closure of the set theoretic image. So in this way, we recover like a closed irreducible subscheme inside the character variety. And using a similar strategy, I can recover like distinguished closed subschemes, irreducible closed subschemes for higher rank character varieties. So yeah, so when I started to work in this connection with character varieties, I was actually expecting to recover irreducible components of these character varieties for pre-abelian groups, but with further reading, I realized that these character varieties were already, they are irreducible as a whole. So yeah, so the best thing I could do was to obtain this string theoretic image, but yeah, as a closed irreducible subscript. But in any case, I think it's really interesting because it points to a connection between another connection between character varieties and tensors. So yeah, that will be all. Thank you very much. Are there any questions?